Okay, we're going to discuss the polarization of light, but specifically how we can look at this using Python, and in this case, it's a Jupyter Notebook. So we're starting with this general expression here, E of r is E naught, e to the I, kzz minus omega t plus phi x. Notice that that defines a wave vector k along the z direction, 0, 0, kz. So in the phase, the k dot r term only gives us a kzz. And this term here, phi x, is a general phase difference that applies to all components of the wave. And all it does is just provide a time or a position offset. Throughout these notes, I'm going to assume it's equal to 0. Now, given that the wave is traveling along the z direction, we get that from the direction of the wave vector k, we know that E0 and E itself must be confined to the xy plane. The field is always perpendicular to the wave vector, and therefore, when we take the real part and resolve out, we get the following expressions for Ex and Ey. You'll notice that we've got the same phase, kzz minus omega t plus phi x, but then between the two, we've introduced this phase difference phi, and we're allowing different amplitudes or magnitudes for the x and the y components of the field. Those are the two things that matter when you're thinking about polarization. Phi, the phase difference between the two components, and the relative sizes of those components. So let's see what we can do. So we start here with the first cell where we set up matplotlib and import some libraries. I'll just run that. And now here, this second cell, I'm just setting up some physical parameters. So I've got the wave vector k. I've set it so that it's got a wavelength of 1 meter. We've got omega. The angular frequency is 2 pi, so that means that the frequency is 1 hertz. That gives us a period. I'm setting up 1,001 time points and a total time of 2 periods. And I'm setting an arbitrary z position to look at the wave over time. Okay, so now let's think about different types of polarization. The first one we're going to consider is linear polarization, and that's where you have a phase difference, phi is equal to 0 or equivalently pi between the x and y components of the field. So you see here that we've set phi in the linear case equal to 0. Similarly, phi x, that phi is always going to be 0. Have I got that right? Yes, we have got phi between the components and phi x overall. Okay, so phi x will always be 0, and then phi will vary depending on the type of polarization. I'm setting the x and y components to have different magnitudes, 1 volt per meter and 2 volts per meter, and I'm just going to calculate the values of the field for all times here in this parade time, which we set up here using linspace covering 2 periods. So if I run that, we can then plot it. Now, there are different ways of plotting the field, and this is important. The first plot we're going to see here is where we're plotting on the x-axis we have time, and on the y-axis we're going to have the amplitude of the two different field components. So let me run that cell and plot it here. So here we have time in seconds. You see that we're going for 2 seconds, which is 2 periods, and you see that the x component has magnitude 1. That fits with what we've defined up here, and the two are completely in phase. They're both at the maximum point at the same time. They both pass through 0 at the same time. They pass through the minimum point at the same time, and so on. So this is plotting the two components individually against time. What we want to do when we're thinking about polarization actually is to plot the fields in the xy plane. So what that means is we're going to be plotting for all points t, we're going to be plotting the position of the field vector tip in the xy plane. Let me do this. And what we see here is that the tip of the field vector is confined to a line, and that's why it's called linear polarization. If we look back up here at the sign plots, you can see that at t equals 0, we're starting at the maxima, so that's going to be this point here on the graph, and then we're going to come diagonally down through 0 down to the minimum and then back up again. And so this is what's happening over time for the linear polarization. It's plotted in the XY plane. Later on, I'll show you some 3D plots. Now, what you can do is you can change the relative magnitudes, and I'm sure you can understand that if we were to change the relative magnitudes, that would change the angle of this line with respect to the x or the y axis. So if the y component had 0 magnitude, then it would be an entirely horizontal line. If the x component had 0 magnitude, it would necessarily be a vertical line in this graph, and so on and so forth. You can change that by changing the values just up here. You can change them and rerun it if you want to. All of these notebooks are available on the course pages, but also on a GitHub repository, which I'm linking to in the comments on the video. So that's linear polarization. Let's think about circular polarization. You could describe it as more specialized. It's probably equally specialized. The phase difference is what matters. This time it must either be pi over 2 or 3 pi over 2. And for circular polarization, we have to have an identical magnitude. Ex must equal Ey. That's what's set up here. We've set up phi circ is pi over 2, and here are the two magnitudes, E both equal, and then we calculate the values over time. So if I run that and plot it against time, you see here we have exactly very similar plot to what we had before, except that they're pi over 2 out of phase. So the Ex starts at a maximum where Ey starts at a minimum, and Ex then reaches the minimum a little after Ey. That's what you expect with a pi over 2 phase difference. Let's plot it in the xy plane, and not surprisingly, we have a circle. Notice that I've plotted this, I've used this command here, plt.axis scaled. What that means is the axes have the same length in the plot as they have physically. So that's what gives this a circular shape. If you didn't set that, you might end up with a sort of a slightly squashed shape. I've also put 4 points here at successive times going around the circle, so you can see the sense in which the orbit goes, or the movement of the field vector goes. If we had phi was equal to 3 pi over 2, it would go in the opposite direction. And again, you could test that by downloading the notebook and changing this line here and rerunning. And you can see here's the code where I've set the snapshot time to be either 0 or the equivalent of pi over 6, pi over 3, pi over 2. So for circular polarization, the tip of the field vector traces out a circle in the xy plane. So if you're looking along the axis of propagation, which in this case is the z-axis, you'll see that the tip of the field vector goes through a circle. Again, I'll show you this in 3D slightly later. Now we turn to elliptically polarized light, which is the most common form, simply because it's not hard to arrange. Any kind of phase difference that isn't an integer multiple of pi over 2, any kind of difference in the magnitudes of the field vectors gives you elliptical polarization. So the first case we'll consider has a phase difference of pi over 2, which might make you think, aha, this is going to be circular, but then we have different magnitudes 1 and 2, so it isn't circular. That means it's going to be an ellipse. Let's plot this, and we see, okay, here's the plot against time. Compare that actually to the circular plot, and what you see is the only difference is the magnitudes. That's not surprising because that's how we set it up. Now let's plot this in the xy plane, and you see that what we've got is the same as we had for the circular motion, but we've stretched it along y, and that's because we've set the y magnitude to be twice the x magnitude. Okay, so that's a very simple, almost a trivial example of elliptical polarization. The other way we can do it is to have equal magnitudes, but a non-integer multiple of pi over 2 for the phase. In this case, here we see we've got the same magnitudes, but the phase difference is just non and half integer. And when we plot that in the xy plane, you see that we have an ellipse here. And the angle, as it says in the text here, the angle of the ellipse, so if we took a line down here, that's the semi-major axis, the angle that makes with the x-axis is determined by the ratio of the amplitudes. And the difference between the semi-major and the semi-minor is determined by the phase difference. So if the phase difference phi was equal to 0, we would be going back to linear polarized light, and so this semi-minor axis here, that is the shortest distance across the ellipse, would go to 0, whereas the semi-major would be at its maximum value. So you can see that as you change the value of phi, the shape of the ellipse will change. And in fact, if we go a little bit further here, where we have general elliptical polarization, you can see that we could play with that very nicely, and you could change this phase difference here, you could change these magnitudes, and what we have in the xy plane again is a situation where it's just twisted relative to the axis. And notice again, I've got this scaled plotting so that it's got the same aspect ratio on the axes. So for elliptically polarized light, what we're finding is that the tip of the field vector traces out an ellipse in the XY plane. And the angle and the size of the ellipse will depend on the phase difference and the relative magnitudes of the field vectors. Another thing that we can do, this is another little bit of Python here where I'm going to plot out a series of snapshots. So what I'm going to do here is I'm going to iterate over 100 time points, and at each point I'm going to plot the ellipse, but then I'm going to put a dot where the tip has got to at that time. So let me plot that. So here you see what I'm talking about. For every case we have the ellipse which is traced out, and then we shift around the ellipse over time. So you can follow that through and watch the way that the tip of the field vector is effectively orbiting in the way that I'm showing with my cursor. This is quite a useful kind of plot that you can use. You could play with the overall phase phi x here. The only thing that would happen would be the starting point would change if you did that. Finally, I'm going to plot in 3D. I'm sometimes a little bit wary plotting in 3D because you can hide an awful lot. It doesn't always help, but I think in this case there are some things that you can use. The command you might want to look at is this one here, which sets the viewing point, gives you the elevation and the azimuth. So let's plot the linear polarization here. And here we see it. So on the sidewalls here, on this sidewall here, you have x against time. On this sidewall, you have y against time. In the bottom here, you have the xy plot, and that's the one that we had all the way back up here. If we go back to linear polarization, so there's the xy plot, and then these are the two plots we're seeing on the sidewalls. Now we're going to come back down again, and then in orange you can actually see the position, the path of the tip of the field vector against time, plotted in 3D, and it's very easy to see that the field vector is confined to a plane, and when projected down into the XY plane, when we ignore time, it's clearly confined to a line. Let's do the same for circular polarization. Okay, so again, we have the x against t here, we have y against t here, we have x versus y in the bottom, and then in orange we have the path of the field vector, which in this case is a helix over time. And finally, you can do this with elliptical polarization, which looks very similar to the circular polarization, except of course we have an ellipse rather than a circle. So we have still a helix, but it's an elliptical helix. I think that this kind of computational notebook is very valuable because it allows you to experiment with all of the different kind of inputs and parameters and see the effects they have. So I would urge you to do that, to download this, have a look at it, play with the values, let's say with the elliptical polarization, experiment with what happens here. You can always reset, you can download the notebooks again, and it helps give you a good insight into what's going on physically.